Ed Fong is best known to hams as the designer and manufacturer of a range of affordable high-performance antennas, including the TBJ1 and the DBJ1, DBJ2, and the DBJ UHF antennas. More than 23,000 of his antennas have been sold. In his day job, Dr. Fong teaches at the Silicon Valley campus of UC Santa Cruz. His 25 years of experience in RF systems, data conversion, and analog design include work at L'Oreal, Microsoft, and National Semiconductor. He holds 12 patents and has published more than 40 scientific papers. He uses the proceeds from sales of his antennas to support the RF Wireless Group for students at the WSSC Silicon Valley campus. And without further ado, Dr. Fong.
Thank you, Bernard. So let's see, I'm going to share a screen. Fantastic. Thank you very much, Bernard. And thank you for the club here for inviting me. I've been teaching now for 30 years. Well, we've got well over 30,000 antennas. So they're used throughout and pretty well known. And it's good for me because I don't worry about money for my group anymore. This is our fundraiser. It does, as long as they're willing to work, people can put themselves through school. COVID's kind of slowed us down. So I end up doing a lot of the fine tuning because we can't meet as a group at my house anymore. We used to meet twice a week in the mornings, 2 days out of the week in the mornings, and put things together. And I would still tune them. But even then, they would help. Now I just have to kind of piece out stuff. They bring it home, cut wire. And so I've got more responsibilities. That's okay. It's ending soon. I'll try to condense this to about an hour. And it's just one of the talks we give. This is the introductory one of how we do convert a standard J-pole into a dual band J-pole. And then we have some other talks that we give, if you like this, on how to get gain, how to make a collinear out of these antennas, then how to get tri-band out of it. And then I have a talk on DMR. And I'm also I've given a talk, but I haven't refined it yet, on this Nano Vna, right? You guys, a bunch of you guys have a Nano Vna. Those are pretty cool. Boy, I tell you, we have an 8753 in the lab here, and we've compared it. I mean, that was an $80,000 network analyzer I bought about 15 years ago. See, in the test instrument industry, 10 years is nothing for a piece of equipment. I mean, they're so expensive. It's not like a PC you can buy every year. So we still use that. Don't get the tiny one, get the 4-inch one. It's well worth it. It's a later model. The PC board's much more refined. The layout's much better. So you'll get, this thing will go up to 1.5 gigs. Virtually all of them I've seen. It's very, very good. They're all very, very consistent. They'll go up to 1.5 gigs. And they also have a 3 gig one now, if you're interested in a 3 gig one. And they're cheap, right? $50-$60. You can't beat them. And they do work very well. Once they're calibrated, they work very, very well. Anyway, I've got this talk on my version of the history of handy talkies. So what we're going to do here is we're basically going to go through the article that I did in 2003, February. That was the original introduction of how you actually dual band a J-pole, single band J-pole correctly and have it work. And just various versions. This has appeared it's in the ARRL Antenna Classics, in Volume 8 Compendium, Volume 3 Compendium. So it's been around. It's been around for a while. So here's the articles. The original one was here. The DBJ1, a dual band J-pole, a VHF, UHF dual band J-pole. This is the roll-up version of one. This is the latest one, tri-band one, which does 2 meters, 220, and 70 centimeters. So that's a talk in itself too. And that's my daughter here. 4 years ago. She's just finishing off her master's in mechanical engineering and also a master's in electrical engineering. And then we've also had to patent a lot of our recent stuff. I didn't originally have the idea of patenting these until there's a lot of copycats. When we did the DBJ1, that's a form of flattery. So people are copying, it must be decent. But what I didn't like about it, so we started buying these copies and we couldn't find a single one that worked very well. They didn't understand exactly how it worked. So they just kind of went by the dimensions we had in the article and started selling them. And I mean, they were resonating at 155. One was resonating at the marine band, because there's a lot of little things you have to understand. And we explain in the article, but these copycats that we found really didn't pay much attention to them. I didn't like that they weren't copying it correctly. So our attorney over at the university says, you got to patent this stuff, and then you prevent the copy. So we did patent the tri-band one. We did patent how you get gain out of a J-pole. Okay, so why did I choose a J-pole to begin with? Why didn't I choose the ground plane? Several reasons. No radials, right? Ground planes. I grew up in the 60s, so we had little ground planes that we would make out of SO239 connectors, flip them over, get some number 14, sometimes number 12 wire, and solder on some radios, and I thought that would work. And SWR, in fact, when I was in high school, I thought SWR, that's all you need to know, right? Once the SWR is good, you're fine. No, it turns out you go through electrical engineering school, go through antenna design grad school. SWR just tells you the matching. It doesn't tell you the performance of the antenna. Well, J-pole actually has a pretty good performance antenna. Plus, it has no radials. Radials, you kind of want to avoid these days. What we find is that if you put up an antenna, VHF, UHF with radios, they don't hold up very well in high winds on a tower and things like that, because they're torqued. The radios, they've got torque on them. Gravity's pulling them down. So eventually over the years, they'll fall off. So if you can avoid that, get a good design going without it, that'll be great. And also a vertical J-pole has a pretty good ideal dipole pattern. A ground plane does not. A ground plane tends to a little higher angle of radiation. And what's the difference? About 1.5, 1.6 dB. So if you were to compare a true vertical half wave, a J-pole is one, compared to a ground plane with a ground plane quarter wave radiating element with ground radials, you'll find that it's about 1.5, 1.6 dB less signal at the horizon. And that's what you're talking about. Horizon is pretty important. So you get about 1.6 dB better pattern, at least on the ground, with a vertical dipole like a J-pole. But then the J-pole configuration, the other nice thing is it's end-fed as opposed to a dipole. Well, we'll get into this. Like here's a perfect example of a modern tower. Took this a few years ago up in Sutro Tower up in San Francisco. That's like the main tower in Twin Peaks. Bunch of antennas. This tower in particular is not broadcast, but commercial two-way radio. You can tell these are two-way radio antennas with some microwave links. If I would have taken the same picture 20 years ago or 30 years ago, you would have seen a lot of ground planes. And when you recognize them, of course, you'll see little ground radios. Well, I even look at this really carefully. I don't see a single antenna there with radios. I mean, slowly over the years, they've eliminated it, which means there's some kind of vertical dipole or J-pole design. So pretty much these days, everything's gone with either J-pole configuration or a variation of it. Overall, it just works better. Now, the disadvantage, of course, is it's 3/4 of a wavelength tall. It's a half wave with a quarter wave matching section, as opposed to a quarter wave ground plane. It's only a quarter wave tall, but then it's got radials. And you figure, well, which is better? Initially, if you look at it, it's not clear. But no, over time, it's very clear that you can tolerate, especially at VHF and UHF, because it's not that tall. Right? You can tolerate a complete 3/4 wave vertical better than you can tolerate a quarter wave vertical at radios. With radios, again, they fall off. The maintenance is just much higher on that. See, here's a close-up zoom-in view like a vertical dipole. It's not a J-pole, but a vertical dipole. You wouldn't see this very much neither. Years ago, you guys, you old timers who knows the repeaters. We used to have 4 bay. It used to be 90 degrees each. I guess you had 90 degrees. There'd be 4 of them spun around for repeater antennas, and then you would have a matching harness. I remember playing with these. I mean, conceptually, it's pretty cool. Practically, I mean, if you want a configuration like this with 4 of them, each at 90 degrees apart, it takes quite a bit of effort to build it right with the phasing harness and then putting it up in a mountaintop that would have freezing ice and hot in the summer. It's got to be it's not simplistic enough to be durable, right? Most durable things have to be fairly simple. Either it fits all into a PVC pipe or radome or something. This got exposed. And again, a lot of connectors, right? If you need 4 of these to form a 4 bay dipole, you need a bunch of connectors, at least 4 connectors up there, and then combiners and things like that. And it's just too much of it's exposed. If you get them to work right, they work. Of course, we use these for repeaters in the 60s and 70s, but these days you don't see too many people using these. Again, the reliability and a simple explanation for the reliability is here's a dipole, here's a piece of coax, and then there's an insulator right there. So one side goes up, one side goes down. That's a dipole. But look at what you have to do. It is a halfway vertical dipole. But look at what you have to do if you choose this configuration. You've got to feed it at 90 degrees. That's kind of a hassle. You got to feed it not at the bottom, but at 90 degrees. That means you have to have an arm of some type. And this arm causes torque. Right? If you're a mechanical engineer, you know that there's a torque point right here, R cross F, the weight, and then the force times this distance, the R. That puts pressure or tension right there. When the wind blows, that force is magnified by R cross F. So these things over time, you know, they don't hold up very well. And the better performance of the antenna would be if you would get the longer the arm is further out, the better performance it would be because it will be away from your mass. And you know, if it's on a top of a mountain, it's going to be a metal mass that's going to act as a reflector. So you got to get pretty far away so it doesn't disturb the pattern. The further you get away, the larger the R cross F, the more force. These won't last. Unless you build them really durably with steel, and which I've seen people do, then it gets very expensive. So if you use vertical standard dipoles, center fed, which is, you know, the low impedance point of a dipole, it's quite a hassle, as you guys know. The further you get this out, the better the antenna will perform, the longer the arm, but then the more torque, which means be more vulnerable to wind and all this stuff in the elements. And then again, if your mass is a conductor, it will always act as a reflector. Even if it's 2, 3, 4 feet away, it will act as a reflector. So although we did it 30 years like this, I think there are better ways of doing it today. And that's why you don't see this configuration as often. And they were expensive. You know, 4-bay dipole, $800 for a good commercial one, because you have to build it really, really durably because of the way it's physically constructed or configured. Okay, so I looked at this Jpl thing. This is back 30 years ago when Danny Monticelli, AE6C, showed it to me. And I tried one out. He just built it out of twin lead at the time. He said, hey, take this home. It's a swap meet. I first got introduced to this Jpl thing now 30 years ago now. And when I started trying, I go, wow, this thing actually works pretty well. I didn't understand at the time. But you first try something out, and if it works well, then you say, hey, why does it work so well? And in fact, when I was first introduced to it with it just in a ribbon J, it was just hanging in the air. And I said, well, you know, it works so well. We should make this a permanent antenna. So I stuck it into a PVC pipe, recalculated the velocity factor, because when you put it in a pipe, the dimensions have to decrease. And a lot of my students says, why? You know, a lot of people say, well, it's just RF. It doesn't conduct DC. I mean, it's an insulator PVC pipe. But you RF guys know that that's not true, because a wave transmits, and it goes by basically fundamentally a different equation, which is C equals F lambda. The speed of light is equal to the frequency times the wavelength. That's a pretty standard antenna design equation. And that C, if it's in air, you can use, you know, the speed of light, 3 times 10 to the 8th meters a second. But once you put an antenna in water, in a radome, even inside a house, right? You guys probably might not have noticed this. If you bring an antenna that's working perfectly outside, you know, VHF, UHF, you bring it inside the house, and the closer you move to objects, the resonant frequency goes down. One of the simple explanations for it is you slow down the speed of light. You know, it doesn't radiate in a vacuum anymore. So if you cover it like in a complete PVC pipe, it'll slow it down by 3%, 2, 3, 4% in that range. So you have to compensate for that. And so instead of C equals F lambda, C, instead of using 3 times 10 to the 8th meters a second in that formula to calculate, you know, what lambda should be, you got to decrease it by 3 or 4%. And that's the case. You'll decrease 3 or 4% of the lambda, the wavelength. So I'll give you a quick example. Water is about 0.5. Now, in other words, if you shine light through water, it will slow it down by, you know, approximately half. So an antenna, if you distill water, if you're making an antenna, though, take, for example, 2 meters, you know, 18, 19 inches. If you're to totally immerse that in distilled water, it will resonate at about half the length approximately, because it slows down the speed of light. So in other words, if you stick in the antenna into a PVC pipe, you'll have to shorten it by 2 or 3%. Otherwise, it'll resonate 2 or 3% lower. But the good thing about sticking it into PVC pipe is this new stuff lasts for years, 30, 40 years. In fact, the problem is you can't break it down. They're trying to find ways of, you know, the PVC and vinyl windows and all that. What do you do with it? When you're done with it, how do you dispose of it? That's still a problem they're trying to figure out. Is there a way of reversing that process? You use your antenna analyzer, and you try that sometimes. Get an antenna, it's operating in air. Jpl is a good example because you can hang it. Get your analyzer. Oh, this isn't resonating at 146 megahertz. Put it into PVC pipe. It'll go down to about 143, 144. Because by wrapping the antenna around with anything, in this case PVC pipe, you slow down the speed of the wave travels. But the advantage is you have to do this because you couldn't hold up twin lead or wire, you know, up on a hill on a repeater site. It would just get torn apart during the winters. And during the summers, the UV light would tear it apart. So you have to cover it. So there's no problem with covering it. But if you do have to compensate for it. But that's very simple, right? You just have to put your analyzer on it and recompensate it. And you'll see the pattern is that the more stuff you put around it, the lower the resonant frequency will go because you're slowing down the speed of light. It's got to be non-conductive, of course. If it's conductive, you've shielded it. This is a non-shield. This is just the velocity factor. So this is kind of an old slide here. But yeah, we've done about 30,000 of these now. So we're going to go through this. So that was a standard Jpl, and I'm sure you guys, do a lot of you guys use Jpls now of some configuration for VHF?
Yeah.
Yeah, we've really converted in the last 20, 30 years. When while I was growing up, it was ground planes because everyone else was using ground planes. But no, pretty much some kind of a Jpl. They've got the copper J, what else? The ribbon Js and all this. I think people are pretty convinced that although it's 3/4 of a wavelength tall, it doesn't have radials and it's end-fed. Those are real advantages. So what we're going to discuss here is I'll go through the basic Jpl, very basic, but the main discussion is how do you make a dual band without getting any losses? With a dual band still perform well, hopefully half wave at both VHF and UHF. So what's interesting was back in the 1990s, mid 90s by then, a lot of these repeaters, you guys are in LA, so we started getting a lot of UHF repeaters because the 2-meter ones are pretty filled up. And a lot of the handy talkies were dual band. Lenko's was offering them, ICOM, all the Yaesus, they were all becoming dual bands and dual band mobiles. So people wanted a good dual band antenna. Not to say that they didn't exist, you just had to pay for them. A good diamond or something run you $100. So the goal here was everyone's asking me at the swap meets, hey, I've got a Jpl and I've got some 2-meter antennas. We notice it works at UHF, but not very well. In fact, let's see here. They work because most antennas, virtually all antennas, unless you make them special, typically resonate at odd harmonics. In other words, if you build a simple dipole, 100 megahertz, just as an example, if you put an SWR analyzer on it, the SWR will go down every odd multiple. In other words, 100 megahertz antenna will resonate at 300, 500, 700, 900, etc. And you can prove that very quickly by just drawing the waves on an antenna. If you were here, it's very simple because every time you add a half wave, you return to the same spot. So that's why a VHF 2-meter antenna will resonate at UHF. It's a third harmonic. I didn't say it would work well. I just said it would resonate. But if you actually used a vertical, whether it's a Jpl or whether it's a ground plane, VHF one at UHF, at its third harmonic, you measure the SWR, it's okay. But if you start observing and start using it for a while, you'll notice that it performs quite poorly. In fact, if you were to quantify it, it performs about 6 to 8 dBs worse than just a regular half-wave antenna. So you lose about 6 to 8 dB if you hold it up vertically and you use an antenna at its third harmonic. And we'll show you this I'll show it to you later. No, here. Okay, just go to this slide. Here's a good example of an EasyNet simulation. You can do this on ADS, you can do it in FEDCO. I think all of them, a simple model like this will always show something like this. So this is imagine this is the elevation pattern where this top is the sky and this is the earth, and you imagine yourself holding an antenna there. Basically, the fundamental would be this figure 8 pattern, so that if you're looking down from the sky, it's great because it's 360 degrees. It looks like a donut, and it gives you good 360 degrees coverage. In fact, this is quite a desirable pattern because you would think you would have a sphere. No, this is actually a pretty desirable pattern because it forms a node at the center so that this energy isn't wasted in the sky. It's a figure 8. That's exactly what you want, a figure 8 pattern looking at directly, because here's the transmitter, you're standing here. You're not up in the sky. So actually that's a pretty good pattern. In fact, a dipole that's why it gives you a 2.1 dB gain over an isotropic antenna. In other words, over a spherical radiation. So a vertical dipole is actually a pretty good pattern that you want on Earth, because if it's hanging vertically, it basically radiates a figure 8 pattern, not a spherical pattern. If it was just a pure spherical pattern, a lot of the energy will go up in the sky, and that's not what you want, unless you're talking to the space shuttle or something, or International Space Station. But now, if you take the same antenna, fundamental, a good example would be, let's say, 2 meters, and then you take the third harmonic, which would, in our case, would be UHF, the pattern looks like this. Again, this is the sky, that's the Earth, and here's the elevation you're standing, here on Earth. Well, here it's about 45 degrees lobes. We call this a 4-leaf clover pattern. If you were to actually integrate this or measure it, 75% of that energy is here, and only about 25% of it is left here. Well, you want it here because this is the elevation pattern where the transmitter's here and you're standing somewhere over here on Earth. You lose about 75%. Now, a little bit different if you're flying on an airplane here. Great, that works fine. But if that's not your purpose, this is not the antenna to use. In other words, not to use a fundamental antenna like 2 meters on a third harmonic, because a good 75% of the energy goes right up into the sky. So we're going to try to fix that. What we ideally want is we want the fundamental to be a nice figure 8 like that, and we also want the third harmonic to be like that, all in one antenna, because this way we don't get the losses. So let's see. So I'm going to come up with a design like that. Could you do this? Could you do this in a simple manner in which you can communicate to people, like in a QST magazine, that they can do it too? You probably, with enough money, you can do anything. You can land man on the moon, but this is not the purpose. Could you modify all the antennas up to the Jpl, the ground planes? Can you come up with a principle where you can also have it go UHF, a VHF antenna also work at UHF and work well, work like a half-wave dipole? So I tried all kinds of things. So here, I think you understand this pattern, what we're trying to get at. I tried all kinds of things. Well, the first thing you got to remember, you just don't try random things. The fundamental principle of an antenna is based on the Smith chart. You have to understand that a Smith chart represents a half wave of transmission for a given frequency. And if it's from 0 to 180 degrees, that's a quarter wave. And the top is inductive, the bottom is capacitive. You don't have to know this for the explanation up here. All you have to really understand to understand how we did this dual band antenna is that if it's a 0 ohms on the left-hand side, when you go a quarter wave around, which is 180 degrees, it becomes infinity. The impedance, not the resistance, but the impedance. A lot of my students get that confused between impedance and resistance. Resistance is DC, impedance is AC. That's for the impedance. And similarly, an open circuit, which is infinity, right? An open circuit stub. Let's see, I must have a stub here. Hang on, let me get you a stub. Here's a piece of coax. So it's about 5.5 inches. Oh, that's just a quarter wave at UHF, about 5.5 inches. If it's an open circuit, You know, I haven't shorted anything, open circuit. What does it look like at the other end at UHF? Well, the Smith chart says if it's an open circuit, infinity, if you go a quarter wave, which in the case of UHF is about 5-6 inches, this thing's going to read a short. It will really read a short at approximately 450 megahertz. That's how waves work. It's not DC, and that's the most common misconception when I get new graduate students. They confuse DC, resistance with impedance. So that's all you have to know here to work on this antenna. I mean, we spent almost an entire quarter on Smith chart designing amplifiers with it, matching and all that. But that's all you need to know for this talk we're giving here. So just keep that in mind. So here's how a Jpl works. And I like, again, the Jpl is end-fed. It's end-fed. How does it basically work? Here's the 38 inches. This is the twin lead. So you really can ignore this side. This is just like a TV twin lead for just drawing purposes. So normally you would feed it from the middle, right? If you, again, that picture we showed of that dipole, you feed it in the middle. Again, then you have to have an arm, you have to have a mass. Can we get away with it? Is there a way of getting away from this? Well, the reason why it works is because in the middle, it's a low impedance point of a dipole. The ends of a dipole are high impedance. They're high impedance. And our handy talkies and our mobiles were not high impedance. We're like 50 ohms. So how do you get it to 50 ohms? How do you get this end part, which is high impedance, down to 50 ohms? Because you can't feed it here. Naturally, you need to feed it in the middle where it's low impedance. So you need some type of impedance transformer. And that quarter wave stub I just introduced to you is the ideal piece. Short circuit on one end, short circuit on one end. If you go a quarter wave, which is 180 degrees to the Smith chart, it's an open circuit. Maybe not infinity, but pretty high. It's several thousand ohms as opposed to 50 ohms. And the same goes for the end of an antenna. It probably isn't infinity. In RF, nothing's infinity, but it's high. Let's call it it's higher than 50, much higher than 50, 10, 20 times higher than 50. So if you can somehow match that high, the end of a dipole, which is high impedance, but also the end of a quarter wave transmission line is high impedance. So you can see if you short this end, you go a quarter wave, it's high impedance, and you put the other end of a dipole, which is also high impedance, the wave that travels through here will find the least resistance because it's matched. It'll just travel right through there. And then you'll see it. So based on that principle, you could say, that's pretty interesting. If that's a short that's 0 ohms impedance, and we go up a quarter wave. So a quarter wave at 2 meters is about, you think it's 18 inches. But again, in this twin lead, it is not 18 inches. It's about 16.5 inches because twin lead has a velocity factor associated with it. It's not an air. If it's an air, it is 18 inches. But twin lead's got plastic around it. That slows down the speed of light. And if you know the percentage, since C is equal to F lambda, you know what to make this piece. And it comes out, it's going to be shorter. Turns out it's about 16.5 inches as opposed to about 18 in air. So that's the matching point for the twin lead here. Well, then you can take this argument one step further. If that's a short circuit, which is 0 ohms DC or 0 ohm impedance, a short circuit is a 0 wherever you go. And you figure it's high impedance here, maybe not infinity, but pretty high, several thousand ohms. There must be some point where it's 50 ohms, and there is, or close to it. There's a little bit of an inductive part, but it's close, pretty close. It's about 1 to 1 1/4 inch. And, I basically find this by just experimenting. Obviously, 50 is closer to 0 than it is infinity. So you can start from the bottom and you start moving up and you find out that point between 1 to 1 1/4 inches. You will find 50 ohms. Again, with a little network analyzer, little handheld network analyzer, a piece of cake to find that point. In the old days, with a SWR meter, it's a lot harder, but with an analyzer, you should easily find it. So that's where you cut into it with coax. And the great thing here is you've got built-in lightning protection, right? In a ground plane, it's a high impedance. Ground plane or a regular dipole, there's no DC resistance between the main radiating part and the ground. It's a dipole. Here, it's a little bit different. The dipole is shorted. You never break it here. DC-wise, this whole thing is, you've got the shield end and you've got the conductive end. It's short. It's a DC short, right? You see the DC short right there. So it's always discharging this element. You don't have to worry about, lightning. You don't need a lightning arrestor or anything like that, because it's always a DC short. Because this is the DC path right there. It always shorts out, which is great. I've convinced some people that were using commercial people, we need a lightning arrestor according to the electrical code. I go, no, you don't. He goes, well, but you need it. You need it. I go, you can't beat this. This is always the DC short. That's what a lightning arrestor tries to achieve, right? At 40 volts or so, it shorts it out. And then if it goes away, it opens circuits. This is a DC short all the time. You can't beat this. You're wasting your money. I've convinced some people that. And that's the other reason why you see a lot of these antennas on towers. It's got a built-in lightning arrestor. It's a DC short. And then you get the other fools that buy your antennas. Says, how can your antenna work? They ohm it out. It's a short. I go, it's a DC short. It's not an AC short. To measure impedance AC wise, you don't get your digital multimeter. You need a network analyzer. Of course, sometimes these people call me, it's a short circuit. I go, well, put your radio through it. It works, doesn't it? Because yeah, it does work. Get it with a DC short. And they say, can you explain that? I go, well, then you got to take my class. Take an introductory class to RF design, and then you'll figure it out. But that's very common. People say it's a DC short. How can it work? Because you're mixing impedance with resistance. They're not the same. But very common among new grad students. And that's how that's how I know when I get new grad students. The guys that know are typically hams. The guys that don't know are the ones that say, I'm pretty smart and I want to make a living. What should I major in? Those are the ones that don't know. And you know what I tell them? If you're going to stay in this field of RF, I don't know how many of you folks are. You're probably, a lot of you guys are engineers down in Southern California, right? I tell you, you're never going to be a successful engineer until you really look at this stuff. I love this stuff. This is just great stuff. I don't read criminal novels or whatever. I don't read Harry Potter at night when I go to bed. I've got a QST or I've got an IEEE journal. Okay, then you know this is your field. But I tell folks, if you're in this because you think the money's good, well, the money's okay, the money's all right. But you're in it for the money and you think you're pretty smart. You probably are pretty smart. You made it into grad school. You know where you usually wind up? Not that they would starve. You wind up, as you guys might know, becoming like, maybe marketing engineers, test product engineers or something. Very routine stuff. You don't get to do the cool amplifiers and the oscillators and the IQ modulations and all that stuff because it's not cool to you. To me, it's just really, really neat. So that's my story. So now you kind of understand how a J-pole works. It's a basic dipole, but it's end-fed. How's it end-fed? It's end-fed because of this quarter wave stub here. The short becomes a high impedance and you tap it off. And then all of a sudden you can end feed it. You can put this in a tube. You can have a PVC pipe. You can have a connector in the end and it just holds up vertically and you just clamp it from the bottom. You don't have to tap it or anything like that, externally. So it's very convenient and it works well. So the idea is, how do you make this dual band? Okay, here's some J-pole configurations. So yeah, I'm sure a lot of you folks have seen the copper J. Again, it's the same principle. Here's the half wave element. You've made the transmission line here. You short the bottom and then you tap it like this. That's some tap a couple of inches above is your 50 ohm point. And this one works well. I mean, we have them here. We try to, in my lab, I'll show you one. Here's a copper J. Here's that tap point, exactly like how you see it. And we try these things out just to see how well they work. And well, we find that this one works pretty well, this copper J. I would say not very practical because that copper pipe is pretty expensive to purchase these days. And you got to weld a lot of pieces. It's got a lot of pieces, the welding here, the welding there. And you can build it and it will work. We built it and it works. It does not you would think it would work reasonably well at UHF. The problem with this configuration is that, at UHF is only 6 inches, right? 5-6 inches for the quarter wave. The problem is you only can get these 2 pipes to make the transmission line so close. It's limited by this T and this elbow, which I think if you measure it here, it's about 1.5 inches, almost 2 inches. The problem with that is at UHF, that approaches too much of a quarter wave. You lose a lot of the signal just by that jump. It starts radiating in a horizontal direction. So if you really tested this antenna at UHF, it doesn't perform very well at all. Not only do you lose the 6 dB because it's a 3/4 wave like what we showed, you also just lose it just by even before you feed it. It's too much exposed. See, at 2 meters, you can kind of get away from that because it's 18 inches. A quarter wave is 18, and this is maybe 1.5, 2 inches. You can get away with it. You lose some, but it isn't that significant. At UHF, you're losing a lot. You cannot expose 2 inches at UHF. I think you don't suffer losses. So this antenna works quite well at 2 meters. Kind of expensive to build. Doesn't work very well at UHF, but that's one that's pretty popular. Then this one here, this is the Arrow, which they start marketing, I don't know, 15, 20 years ago. And we also have one we didn't build this one. We bought it. It was just easier to buy for $50. I wanted to see how well that performed, and it's not bad. I mean, they did their homework. This is the 2 meter section here. The quarter wave transmission line is here with this 19.25 inch section. What they did was they did this. They put in this little piece here, 6.5 inches, to resonate at UHF. So you can imagine it as this at UHF. Ideally, what they would want is this is the main element with the half wave right here, and here's the matching stub, the quarter wave stub, and the short will be at the bottom. And at VHF, this is the whole element, half wave there, another quarter like this. But it's fed with just one connector. If you work out the waves, you can do this. The only slight, and it's quite an improvement. This is an improvement over a standard Jpl being resonating also at UHF. But you can imagine what happens is this is the UHF antenna. This is the VHF antenna. But the VHF antenna, and assume both of them match well, but you only have one feed point. There's only one feed point in these. That means half the energy, if you have a UHF signal, half the energy of the UHF signal is going into here. And of that one, you lose 75% of the energy in the sky. So half of it, you lose 75% of it. The other half is okay. Here's the real UHF Jpl. I mean, you might get some reflections off here, but in terms of efficiency, here's the UHF one. That works fine. So half of the energy, if you feed it through this point here at UHF, goes through the right antenna, but it's the same feed point. The other half goes through here, which is the wrong antenna. So it's an improvement, but it isn't 100% improvement because you haven't decoupled the VHF antenna from the UHF. But it works. I mean, it's okay. You notice we can measure the difference. There's some loss at UHF, but it is by far better than just using a copper J or a 2 meter Jpl at UHF. It's better than that, but it's still not the perfect solution. And then this other solution we see a lot here is the Slim Jim. And I think you guys are mostly engineers. You guys probably know that. No, the Slim Jim does not offer 6 dB gain. You see a bunch of websites doing this. Antenna gain is just not that simple. The Slim Jim is just, they take twin lead and they say, oh, from like our standard configuration for Jpl, just solder the 2 leads together. Just solder together and you get 6 dB gain. You engineers would know, not that simple. No, you don't get gain. You don't get anything. It works, as far as we know, this works as well as any Jpl. Tying these two together just doesn't make any significant difference. And it's confirmed by Larry Siebeck. He passed away a few years ago, but he spent a lot of time trying to tell people, no, he had a whole website. No, it may give 6 dB gain over a rubber duck, but that's not how we measure antennas. We measure it over a dipole, and it's the same as a Jpl. And his website's still up there. I don't know who manages it, but I like it because he really tries to say, hey, don't believe everything you read on the internet. So how do we make a dual band? Now, I think I've given you the background. Quarter wave stubs are an open, a short at one end is an open on the other. So here's how Well, I finally came to a solution where you can go home and implement it. I published an article on it, step by step. You can do it with some patience. It'd be good to have an analyzer. You don't have to. It makes it easier. And I think these days, with being, 50, 60 bucks for one of these analyzers, it's well worth it. I have all my students have it because I give them assignments. You take home little black boxes. I don't tell you what it's in there. You measure it and you come back with the problem set saying, this is what I think it is. So that's pretty cool. And I tell them it's like buying a textbook, right? At 50, 60 bucks, it's actually cheaper than most RF radio textbooks. But you get to keep this. It's also a signal generator, of course, right? If you start and stop it at the same frequency, it becomes a signal generator. So that's a pretty cool device. Okay, so how do we dual band it? We did this. The bottom is the same. We always said the matching at VHF is also the matching at UHF. That's not the problem. See, all it does is this. This is a quarter wave matching stuff, right? Imagine this is the short and the wave kind of goes like this is a quarter wave. Well, at UHF, it's just a 3/4 wave. It goes up a little bit here, and it goes back a half wave. It goes back a half wave like that, and then you have it. So you're back at a high impedance point. Remember, every time you go another circle around the Smith chart, you're back at the same point. That's all this does at UHF. This 16, a total 16.5-inch stub, it's a quarter wave at VHF, but it's a 3/4 wave. You've added a half wave at UHF. It still matches. It goes through an extra turn around the Smith chart, but you get to the same point. So the matching's not the problem. So what is it that you want then? At UHF, you would like, 11 to 12 inches, depending what frequency you're at, 11 to 12 inches for the half wave radiator, but you would want it to stop. If it were just to stop there, none of this stuff on top, it will work fine, because then you wouldn't have VHF, you just have UHF. So how do you have both? Well, you put back to this quarter wave stub thing. You put a quarter wave, in our case, RG174, you can use RG58 or RG8X for higher power. If it's a short up here, it's got to be an open because it's a quarter wave. It's not 5 or 6 inches because it's in coax. Coax slows down the speed of light by, depending on what type you have, 20 to 30%. So the stub actually turns out to be about 4¼ inches or so. It will not be 5 or 6 because, again, it's in coax. It slows it down. So what happens here is at UHF, it's a short here. So what does it see here? It sees infinity. But at VHF, that's not resonant. It's not resonant. The wave just goes right through. In fact, it sees this as just coupling, capacitance, like a piece of wire goes right through and it comes back out here. So at VHF, it sees 11 1/4, 4 1/4, plus the 17 inches. Lo and behold, you add that all up. It's like 37, 36 inches, whatever. It's a half wave. But yet at UHF, you don't see this stuff. All this stuff's on because that isolates it. That's a short, therefore that's an open. It just sees that part. And sure enough, it works. You say, wow, how long did it take you to think of this? Well, if you explain this, it's pretty simple. But it took me a lot of trials of what can I do that's simple, that a ham can follow, that can convert their 2-meter Jpl, or you can use this principle in a ground plane too, and convert it to work well at UHF. And I tried a lot of things too that didn't work, and we did some testing. I remember late at night with friends, does this work? Does this work? Are you reading, the so-and-so reading on this? And we found that this configuration really behaves like very close to half wave dipole at VHF and also a half wave dipole at UHF. Okay, that's a roll-up version. A student of mine 2 years later says, I like backpacking. Can you make this all in one roll-up? Yes, you can. It's just very cleverly done with one twin lead, and you clip it at certain points and you still put the quarter wave stub there. And then you have the coax come out with a BNC connector. So again, yeah, we mentioned the dimensions. So if it's a roll-up operating in air compared to a antenna operating in PVC pipe, it turns out to be 1 or 2 inches shorter in the pipe because of the velocity factor. Let's see. So we tried different pipes. So let me show you one of these antennas. Do I have one? Do I have one in the pipe? Hang on. The first thing I do is, what kind of pipe should I use? Are all pipes, PVC pipes, created equal? So that was a big experiment one of my master students did. It's actually pretty, if you look into it, the velocity factors, what contributes to velocity factor, performance of velocity factors, and loss tangents and things like that, it's pretty complicated. But we're forgetting all the math and the analysis. What we found was this Lowell's pipe, whatever they make it out of, 23990, best for RF. Pretty cheap too. About $2 to $3, depending where you buy it, for a 10 feet section. It's the thinner stuff, obviously, not the schedule 40 has a higher loss tangent. Let's say you're trying to find another material with low RF losses. It's very simple, actually, strong correlation. Just cut a piece, put it in a microwave oven. You guys may have heard of this. Put it in a microwave oven. If it doesn't heat up in 5 minutes, it's probably pretty good. The stuff that heats up, not good. That means that it also absorbs RF. There's a pretty strong correlation to that. And the Lowell's, whatever they put into it, because it's all organic material, whatever they put into it, it does not absorb RF, at least not microwave, and it correlates with RF performance. So this Lowell's 23990, we tried some Maynard stuff. It was okay. At the time, it was Orchard Supply. It was okay, but the 23990 was very, very good. Not that the others were far off. They weren't that far off, but this was pretty good, and it's cheap. So that's a great way to cover up whatever antenna you have, if you want to weatherize it and put it up at a repeater site. Right. So I had another master's thesis guy do on painting of radomes. See, you got to break up all these little things and analyze the hell out of it so people can make a master's thesis. You know why? There's not that many ideas these days that you can do master's thesis on. It's very limited. I mean, we've been doing this since 1960s, right? Antenna design and all that. You run out of ideas. So every little thing, I go, great topic. So he did it on paints, his variations of velocity factors and on radome antennas of various paints. And, it's not that you can't paint an antenna. I know how to paint an antenna, but the way he analyzed it, the way they measured the performance, most of those exercises, how do you measure the performance of antennas? You got to be in an open field. You got to, the general rule is take it 5 measurements, and then you take 5 measurements each time, but on 3 different days of different humidities and different seasons, and then you take the average. So it was the procedure of how do you actually characterize it. It's not that you can't paint it. Painting was the easy part, but how do you analyze it? So our conclusion was that if it's a non-conductive paint, you're probably okay. The most common one, easy to use, that's relatively available is Krylon. 1 coat of Krylon, would it change? You would think it's a little thicker when it slowed down the speed of light. It does, but not significantly. It's not until using like a network analyzer, a cheap network analyzer, an SWR meter. It's not until 2 or 3 coats of thick spray paint, you'll start seeing the resonant frequency go down because it's slowing down the speed of light. Now, obviously, you cannot use any of them that claims conductive material. But Krylon, it's amazing. They've got their really cool chrome. It's not conductive. They've got that chrome paint you can buy. It looks like it's really metallic. It's not conductive. Whatever it is. It looks like it's metal. It's not. We checked it out. I mean, I think there's some other manufacturers that do have conductive. If it does, well, you can't use that. It won't work. It'll shield it. But Krylon, all the colors seem fine. 1 coat, whatever the difference is in lowering the resonant frequency, it's small, not insignificant. We can measure it. We can measure it on our equipment because even if you take a MFJ, right, goes down to the kilohertz. So you'll see if you're very, very careful. You see, before I paint this antenna, it resonated exactly at 146 megahertz, 146.000, and sure enough, if you spray paint it, it will go down. Very slightly, but who cares? 1 or 2 kilohertz, it doesn't matter. But it's measurable. It's measurable, but it's not significant. Here's a regular 2-meter Jpl unmodified at UHF. And here's the plot. This one's done on my 8591 spectrum analyzer. And if you use our antenna on the same spot, by the way, this is nothing fancy. This is just out in the parking lot on a Sunday where there was no cars. We did this test. And with our antenna, with that little stub, same antenna. We tried to make it as identical as possible in PVC pipe and everything. Sure enough, you get back 6 dB gain. You really do. That's a lot. 6 dB is 4x. It's like your 1 watt handy talkie turned into a 4 watt handy talkie. So although we never measured the exact fields, with a helicopter or drone, we simulated it and we measured it at least on the horizontal, on a parking lot. You get back to 6 dB, which is significant. It's fairly, when you think about it, fairly simple, right? It's a fairly simple concept. You just have to get all those dimensions just right. That's the tricky part, getting it all correct, getting it all resonate. But yeah, and then here's the actual measured data. Again, when you measure data on antennas, what you want to do is do three different days. Hopefully one overcast, a sunny day, and then maybe a very cold day or something. And each of those days, try to calibrate everything and take at least 5 measurements, And then that data is probably pretty solid. That should be pretty solid. So this is the average. Pretty confident with these numbers. These are the average of 15 measurements, 5 measurements on 3 different days. And here's the results of it. So here's visual, just one spot. But if you take all these measurements, here's the top one. Take a quarter wave. We learned a lot from this too, at least my students did. You take a quarter wave mobile antenna. It's a whip and using the top of a car as a ground plane. Reference level, we were like 50 yards away. Measuring minus 24.7 dB. It's all relative measurement. We could have normalized it, but this is the actual numbers we get. You can call this zero reference point if you want, but minus 24.7. And you put a rubber duck in the same spot 50 yards away, you, at least in the horizontal plane, you do get about 6 dB. They're right. You do get about 6 dB loss. So when you use a rubber duck at VHF, it is pretty bad. You probably noticed this, but how bad is it? It's about 6 dB. It's pretty bad. If the repeater's strong, you don't have a problem. But VHF is not where you want to use a rubber duck. It's just loaded down quite a bit. And you get a VHF J-pole on average. In other words, this is 15 measurements on 3 different days. Yeah, you do get a little bit of gain. See, this is minus 24.7, and this is minus 23.34. You do get some gain. I mean, it's not significant over a quarter wave mobile, but it's 1.5 dB. 1.5 dBs, 1.5 dBs. You can probably hear that on a weak signal, but on a strong repeater, you won't notice the difference. But the difference is there. And yet, when you use our dual band J-pole, the dual band J-pole at VHF, now only at VHF, it's pretty good. Minus this again, average 23.47. And a standard J-pole is about 23.34. This is about 1/10 of a dB off. We lose about 1/10, probably from that stub. We're losing about maybe 1/10 of a dB. It's not significant. This is only after 15 measurements on 3 different days. So what it says is this is a true difference. It's not an error in measurement. Not when you take an average like that and you come up with those numbers. It is a little bit worse, about 0.1 dB worse, our antenna, because we added that extra stub, I think, where the losses are, because everything else is the same. That's where I can account for. Now, how about at UHF? So that's at VHF. So at VHF, we say, hey, we're better than a quarter wave mobile, but we're not quite as good as the standard J-pole. Not quite, but probably good enough. Of course, a lot better than a rubber duck. Then how about at UHF? Here's at UHF. You get a UHF antenna, mobile, and again, you notice it doesn't radiate quite as well. Same spot, but you notice now the reference level has dropped to minus 38.8 dB. It's just 50 yards apart. This is what you measure. Get a rubber duck? Not bad. UHF, a rubber duck, actually, we've done more experiments after this. It says you lose about 3 dB. Actually, what I find is if you have a good chassis and a good match, different rubber ducks with different radios, you can get it pretty close to no dB of loss if you play with it. But typically you get 2 or 3 dB of loss, but it's not like 6 dB of loss. 6 dB at VHF, that's a lot. Then now if you use a standard VHF J-pole at UHF, it's terrible. We measure this now. It's minus 45. The reference ground plane, quarter wave ground plane, is only minus 38.8. Oh man, you're 6 dB. What was it? 5, you're actually 6.2 dB off. Yeah, that's quite a bit. 6.2 dB is terrible. So you never want to use a VHF J-pole or a VHF antenna at UHF, only in an emergency. The only nice thing about it is your radio doesn't blow up. That's the only good thing about it. Your radio is not going to blow up, but its performance is going to be rather poor. And the other exception is if you're trying to talk to the International Space Station, right? That's an exception because all your energy is going up to the sky. 75% of it goes up in the sky. Then you take our little modification there, it's right back on, minus 38.8, minus 38.9. It comes right back up with that little stub. Losing 0.1 dB or so. Yeah, nothing's perfect, but you lose a little bit, but it's insignificant compared to minus 45. It was at minus 45. You use our little technique, it gets down to minus 38.9. You gain 6 dB back. Yeah, you get 6 dB back. So it's well worth that little stub. Knowing where to put these things, it does make a difference. So see, here's our old network analyzer here. We're getting a new one. I just looked at it. It's a 5026. It goes up to 6 gigs. But we've had this for 15 years, and it's been a real workhorse. A real workhorse for me. Of course, now we all use one of these, and for below 1.5 gigs, these are fine. I haven't tried the 3 gig one. I'm sure it's fine too. But yeah, this is a 6 gig one. I don't actually do that much at 6 gig. Most of our work is all done below 3. Okay, what about that stub? What's the trick? It's that stub. So let's characterize that stub on a Smith chart. It's a short, which means the other end should be an open. How much of an open is it? Scan it from 30 megahertz to 1 gig, and sure enough, at 445, it's right about there. It's not infinity. Like what I said, it's very hard to get infinity, but it's pretty high. Right? We're engineers here, and you guys are engineers. Close enough. If it works, if it improves quite a bit, you ship it. It doesn't have to be perfect. This is not perfect, but it's a lot better than being somewhere here. So it's pretty high, but it's not infinity. It's not up there, but that's okay. It still works. And then I want to see how stable that stub was. So here's the same stub, but I put my hand around it. I placed the shorter end without effect. Yeah, it doesn't affect that resonant point too much. If I put my hand around, of course, it affects other areas, but it's pretty stable. I'm pretty confident. It's because it's a stub floating, and you figure how stable is it? It's fairly stable at the resonance, stable enough. And then I looked at the stub at 146 megahertz. 146, of course, it's a high impedance right about there. And I looked at a piece of wire at 146. It looks like that. So I figured, it's probably pretty good. You can't totally ignore it, but it doesn't affect it that much at 146. But it does affect it. It is a very high impedance resonant at 445. So it's doing its job. Not perfect, but it's fairly simple, easy to implement, and you almost gain 6 dB out of it. So here it is. Again, end fed in my house. It's full vertical, nothing torques much. You end feed it and you tie it down at the bottom. That's a pretty durable connection like that. And here's our roll-up, the roll-up version of it that we make. This is the antenna part. And then we include a 6 feet RF extension because if you're camping, you want an extension. So we design it where it's a BNC connector, and then later we include the adapters, BNC to SMA or BNC to SMA, male or female. That's kind of included in the kit. We give you pretty good prices on the antenna, $32 for the base station one, the roll-up kit, which includes the 6-foot extension and all the adapters, again, $32. The tri-band is $65. I will send that down to you with the PVC pipe because we adjust the coils, and it's just safer that I send all complete pre-tuned. And then some adapters if you want. So anyway, hey, this is the end of my talk. How about questions?